Hello everybody, welcome to the next video on the series of Physics at Home. In this video, we're going to talk about two items. First, we'll consider of capacitors connected in either series or parallel. And the second item is when a capacitor is connected with a resistor. Okay? That is the combination that we're going to experiment and have a demonstration later. Look at here on the left side, we see a capacitor in series circuit. So being the positive terminal of the power supply is here, it attracts electrons from the left plate of the capacitor 1. So the capacitor 1's left plate gets positively charged. It pushes the protons out from the right plate, so the right plate of the capacitor 1 becomes negatively charged. The protons which are lost from the right plate of the capacitor 1, they go and sit on the left plate of capacitor 2. So that becomes positively charged, and then the right plate obviously becomes negatively charged as well. The amount of protons and electrons that are in play are equal number. What that tells is that the charge on capacitor 1 and the charge on capacitor 2 is equivalent or is equal to each other. So that is the first property for capacitors in series, that charge 1 is equals to charge 2. Charges are equal. And at this point of time, we can also invoke the voltage concept. So applied voltage is V, which gets spread out between capacitor 1 and capacitor 2. Meaning the voltage here for capacitor 1 plus the voltage for capacitor 2 is equals to the applied voltage. So the point number 2 is the applied voltage is equals to V1 plus V2. Now at this point of time, let's also talk about the definition or the formula for the capacitor or capacitance. So capacitance C is equals to the charge divided by the voltage. Okay. Now what we're going to do is we're going to take this V equals to V1 plus V2 equation and we're going to expand on it. So if we modify this C equals to Q over V, we're going to get voltage equals to charge divided by the capacitance. So applied voltage is nothing but the total charge in that combination divided by the capacitance in series. This is equals to the charge on 1 divided by capacitance 1 plus charge on 2 over capacitance 2. And as we saw here, is the charges on both 1 and 2 are the same, which is the total charge in that system. So then we can just make this equals to Q, and since they all are equal, we can cancel them out. And we will end up with 1 over capacitance in series equals to 1 over C1 plus 1 over C2, which further can be written as the series combination. Capacitance is the sum of the inverses of all of the capacitors and taking an inverse of that. Okay. All right. In parallel, the charging is again in the same fashion, that the left plates are positively charged and the right plates are negatively charged. But here something unique is happening. Okay. The voltage that is applied will be the same voltage for capacitor 1 and for capacitor 2. As we remember from our previous experiment and also the lab, that because there is a junction here and here, all of these points, they're as good as being connected to the two ends of the battery. Okay. So that will be the characteristic number 1. So the voltage 1 equals to voltage 2 equals to whatever is the voltage applied. All right. Point number 2 here is that the protons that the capacitor 1 loses, the left plate, the ones that it loses, protons from 1 and then the protons from 2, they add up, and become the total protons. Similarly, the electrons that the right plate loses, so electrons from plate 1 and electrons from plate 2, they add up and becomes the total electrons leaving. So either proton living on the left side or electron living on the right side, they both indicate current. Okay, so by definition, by usual, by standard here, usually we don't consider the proton's direction as the current direction. The electron's direction is the current direction. So similarly, in the earlier case, the electrons are moving in this direction, so that was the direction of the current. So anyway, what this entails is that the charge on capacitor 1 and charge on capacitor 2, they add up and become the total charge transfer in the system. So charge total equals to charge 1 plus charge 2. Now let's again look at our original equation, that capacitance is charge divided by the voltage. So capacitance times voltage now becomes the charge, and we're going to use this equation and plug it in number 2. So the capacitance of the parallel combination multiply the voltage applied equals to capacitance 1 times voltage 1 plus capacitance 2 times voltage 2. And as we see from item number 1 here, that this voltage and this voltage and this voltage, they are all the same. So cancel out and we end up with an equation for the parallel combination, which is C1 plus C2. You probably have noticed that the equations here, they look like they are flipped compared to the Ohm's law situation that we saw last week, where the resistors in series and parallel we were trying to analyze. If we remember, then for the Ohm's law, voltage was equals to I times R, right? So voltage and resistance, voltage and current were directly proportional. But if you can see it here, voltage is equals to Q divided by C, right? So we do not have a Q times C relationship for the voltage. And because it's a ratio, then because of which we end up with the two equations flipped in this capacitors combination. Okay. Now in the next slide, we're gonna look at what is RC series circuit. So RC series circuit is just exactly what it looks like right here. So we have a resistor and we have a capacitor. And then what happens is, when you close the switch to create the circuit, then the left plate is going to get positively charged and the right plate will get negatively charged, right? So the capacitor gets charged. And in doing so, if we hook up a voltmeter to that capacitor, then we can measure the voltage as it increases. So the more there will be a charge transfer or charging up of the capacitor, the voltage increases. However, something peculiar about that voltage, and which is that if you plot it, the voltage as a function of time, then it has this trend. So this is a logarithmic growth. Okay. So first it is increasing fast, and then it is increasing, not as fast, and then eventually it slows down. Theoretically speaking, the voltage applied, the capacitor will never be able to reach that. Okay. Theoretically speaking, this black curve here, the plot, becomes an asymptote. Okay. So this behavior here, the logarithmic, or more so actually the natural log behavior, can be given by this equation right here. So in this equation here, R is the resistance and C is the capacitance. Okay, and the time T here is the time it takes. Okay, I mean at a given time, whatever is the voltage. What I want you to notice here is that the V's, this V here is a lowercase and this one is the uppercase. So the uppercase V is the applied or maximum voltage that you could have. The lowercase v is instantaneous voltage. That means when you start, initially the voltage is 0, and then as the time progresses, then you can time it, that at this seconds or these many minutes, how much is the voltage across it. Now in this equation right here, R times C is called as a time factor. So this time factor, we use a symbol tau. Okay, and there is something peculiar about this time factor. So if, or at, maybe let me, I just should say it as at the time factor, at one time factor, at one time factor, tau is R times C, R which is nothing but T. So T we substitute as RC. So RC over RC becomes 1, right? So now this becomes capital V, 1 minus e to the power negative 1. And if you work this out, if you plug this into calculator, that you're going to get, this equals to 0.629. Okay. So meaning instantaneous voltage is about 62.9 or 63% of the applied voltage. So at one time factor, instantaneous voltage is about 63% of applied voltage. So if we have a 10-volt battery and we hook it up to the R and C, then at one time factor, at those many seconds, you're gonna see 6.3 voltage across that capacitor. Okay. And this one is something that we're gonna test. Okay, so what we're gonna do is we have two capacitors and we're gonna create a circuit of R and C1. Okay, for the first capacitor, and then we're gonna measure voltage, and then we're gonna time it. We're gonna measure the time it takes to get to that 63% of the applied voltage value. Then we're gonna repeat the same thing for capacitor 2, and then using the time value and the resistance of the resistor, we should be able to calculate the capacitance of capacitor 1 and capacitor 2. And then once we get the values of capacitor and capacitor 2, then what we're going to do is we're going to create circuits that are going to look like, the R, and then capacitor 1, capacitor 2, a series combination of that, and measure the voltage of it, the instantaneous voltage, the lowercase v. Similarly, we have the same R, but then we create a parallel combination of C1 and C2. And we want to know the voltage. So I'm going to demonstrate this first circuit here and also the series circuit here. And then we're going to see indeed if if we measure measure the values of C1 and C2, can we then predict the C1 C2 if connect together, then the capacitance value here becomes a C series, right? So the time factor is going to be R times C series, correct? R is this one here. And for the parallel combination, then the time factor becomes R times C parallel, right? All right, so in the next section of the video, we're going to demonstrate the two circuits, and also we'll see some calculations. All right, so now on the screen here, you see the three components that we're going to be using. This is a resistor. I have selected a resistor with the highest resistance that is possible, from the stash that I have. And the resistance of this resistor is 119.4. So the resistance is 119.4 and it's kilo ohms, right? So times 10 to 3 ohms. And then I have two capacitors here. So this one is listed as 470 microfarad, and this one is listed as 1000 microfarad. So the smaller one is my capacitor 1, the bigger one is capacitor 2. Now the two probes here that are sticking out, these wires from the capacitors, one is longer than the other, as you can see for both combinations. So for this one, this is the longer, this is shorter. For each one of them, the longer wire is going to represent the positive terminal of the capacitor. And when we are hooking this up, we want to make sure, so for example, when you're doing it here, we have the positive terminal to be connected through the resistor and the positive side here, right, for the capacitor 1. So the positive terminal of the capacitor 1, this guy, the longer wire, is going to be connected to the positive side of my 9-volt battery. Okay. So let's look at this first circuit here. We have recorded R. We also need to record how much is the applied voltage, so that we can take the 63% of that value and then time it, how long it takes for the capacitor to reach that voltage. So let's look at voltage here. .52 volts. Alright, so the applied voltage, which is the capital V, 9.52 volts, and then the voltage at 63%, okay, which is at the one-time factor, is gonna be nothing but, more specifically, 62.9%. So 9.52 times 0.629. So about 5.988, 5.99 volts. 5.988 volts. So approximately 6 volts. Alright, so now let's hook this up together. Alright, so from the positive of the battery, we're gonna hook up to the resistor, right, as you can see here. Then the resistor is going to be connected to the positive terminal of the capacitor, correct? Now what we also need at this point is that the voltmeter to be hooked up to the same terminal, correct? So the same part of the capacitor, so same probe of the capacitor. So it's a bit tricky, but while this one is holding, I open the alligator jaws and then place this one inside. Okay. So that both of the, create a junction there, right? Well, it's not really a junction, but anyway, technically it's a junction, but make sure that, they are firmly together. Okay, so we don't want the capacitor to slip out. Okay, so this lead to slip out. And then the negative side here, also for the negative side, we need the negative of the multimeter. Okay, so as you can see right now, it says there is almost no voltage or 0.02 voltage. So we always want to make sure that the capacitor is drained. Okay, so there is no charge separation. The way we can do that is by, we need to touch the two terminals, so the two leads of the capacitor together. And to do that, I just use a wire. So one end I touch here, the other end I touch here. And you can see on the multimeter, it drops to 0 now. So the voltage is 0. So now this is 0 voltage and it's ready to be charged. Okay, so we need to charge this capacitor, and we want to measure the time it takes to go from 0 voltage to about 6 voltage, which is 63% of the 9.52. Correct. So again, I want to make sure that this is 0. And as soon as I touch it here, you can see, it starts charging, right? So I want to make the connection and start the watch at the same exact instant. Okay, let me train it. Okay, all right. So on the count of 3, 1, 2, 3. All right. Excuse me. So the resistance is about 119.4. So 119.4 exponential 3 multiplied by about 470 microfarad, right? So 470 exponential negative 6. So if you multiply these two numbers, it tells me that about 56 seconds or so. Okay, if it's indeed 470 microfarad capacitance, then around 56 seconds I should expect 6 volt across the capacitor. Okay, so since this is going to be different than 470, we'll see how long does it take, and then using that we can calculate the value of the capacitance of the capacitor 1. So it's getting there now. When it gets to 6, I will stop it. All right, so about a minute and 10.18 seconds. Okay, so this is, as you can see, it's continuing to. So I'm gonna disconnect now. I don't need to charge it any further. So my time 1 is 60 plus 10.18, so 70.18 seconds. Yeah, minute and 10 seconds. I'm gonna repeat the same thing, 2 more times, and then I'm gonna take the average of the 3 values. Okay. Again, before I take it, to the second trial, I need to discharge this capacitor. All right. Okay, so reset. 1, 2, 3. Oops. I think I going to do it 2 more times, and then I'm going to show you my results. Okay, I'll be back. Hold on a few seconds. Okay, so here are my 3 values. Average, $69.86. Okay, so 69.86 seconds. This is the time for one time factor, right? That's the one time factor. So if I look at this here, so one time factor, which is tau, is equals to R times C, which is again R times, sorry, C1 in my case, and which is measured to be 69.86 seconds. So let's calculate C1, which is nothing but the 69.86 over the resistance, which is 109.4 10 to 3, which comes out to be 5.85 10 to negative 4 farads. Which is 585 microfarad. So that is my C1. Okay. Now I'm going to repeat the same procedure for my capacitor 2 and get the value of C2. And then once I have C1 and C2, then I'm going to connect this circuit here, where this is R and then C1 and C2 all in series. Okay. And then we'll time it. And then we're going to see that if we know the values of C1 and C2, then we can predict how much should be the time factor, right? And then we're going to see, you know, how long does it take actually, and using that we can figure out the C series combination and compare the expected and the actual or experimental values. Okay, so be right back. And so after running the experiment, the value for C2 turned out to be 1.2499 10 to negative 3 farad, which is about 1250 microfarad. So my C1 is 585, C2 is 1250. Again, so C1 was written to be 1000, but not exactly, you know, so that's an approximate value here, which is written. So actual value, now we get it from running the experiment. What we're going to do is going to create this circuit now. Alright, so it's the same R, then C1, and see that, you know, for that C1 here, for that positive side, I have to connect my voltmeters positive terminal or the red terminal here. So let's do that. Okay, we have that. And from here to here, so negative of this one connected to the positive of C2, and then C2's negative needs to be connected to the negative side of the 9-volt battery. Now again, you know, this terminal for the voltmeter needs to be hooked up here, so we get the total voltage for the C series, correct? Alright, so there was some left behind charge on these guys, so we could discharge the whole thing. Okay, So now it's 0. Total voltage between this and this terminal here is 0. And then we do the same thing that we did. We time it. So now remember, in the series combination, the C series is sum of the inverses of each and then taking an inverse of that sum, right? And we can expect the C series combination for 5, I think whatever 500 number was it, and then the 1250 for this one. If you take the inverse, then the C series is going to be smaller than the lower one, correct? So meaning that with the same R but then our smaller effective C value, our 63%, the 6 volt, the time it will take to get to the 6 volt is going to be shorter than it will take for the smaller capacitor. Okay? Let's see if it indeed it is true. Okay? So on the count of 3, 1, 2, 3. All right. All right, so it's starting now. You can see now it's increasing pretty rapidly compared to the last one. All right, and so last one took about a minute, so we should expect less than a minute to get to 6 volts. Almost there. All right, 46.95. All right. Okay, so the time one, 46.95 seconds, less than a minute. All right, so at least what we're expecting is getting in the same direction. Let's discharge. Also, sometimes it might help you doing discharging individually. All right, so 0, and then do it again. Okay, I'm gonna do it 2 more times, and I'm gonna show you the result. Okay, so I did it 2 more times, and these are the times here. Took an average of the 3, turns out to be 47.27 seconds. All right, so with that, so now I can take this and apply it to our RC, right? So R times the C series is equals to 47.27 seconds, right? So C series, this is the experimental value, is 47.27 over 119.4 10 to 3. So C series experimental value is 3.959 10 to negative 4. So which is about 395.9 microfarad, correct? And let's see how close this is compared to the C1 and C2, using C1 and C2 what the theory might predict. So C1 was 585, C2 is 1250. So C series predicted value is 1 over C1 plus 1 over C2, and taking an inverse of it, 585 plus 1 over 1250 and comes out to be 398.5 microfarad. This is the C series predicted value. Now let's calculate the percentage. As you can see, it's pretty close, these two numbers. So predicted minus the experimental value. Let's take a absolute difference between the two, and then divided by the predicted plus experimental over 2. Because the predicted value comes from experimental data, so there is some experiment involved in having this predicted value. There's no standard theoretical value. So because of that, then I'm going to take an average between the two and then multiply it by 100. So that turns out to be about 0.6% error. It's pretty good. And that's how this works. So we saw the C1 and C2, and we saw their equations for series and parallel combination, and then we ran an RC circuit using which we figured out the values of the C1 and C2, and then predicted what could be the C series value, and then we ran an experiment with the R and C1 C2 series and then saw how close they get. But similarly, you can also try for circuit 3, which will be a R and C parallel combination, which I can just quickly show you here. So remember, the positive of the C1 and the positive of the C2 should be touching. Okay, so like that. So they need to be connected like this. And the other side over here. Okay, and then once you have these connected, you could either take the probe and then stick it as a three-way sort of combination, or you could also connect it like this. So connect it like this. Oops, giving me trouble. Yeah, connect it like this, and the other end over here, which then having this series, now you can hook it up over here and then start timing it, and then see that based off of your C1 and C2 values, now with the parallel they add up, right? So your time factor is going to be R times C1 plus C2, correct? So because the capacitance is now higher in the parallel combination, it's going to take longer than it would have gotten for the 1000 microfarad, the 1250 microfarad capacitor. Okay, all right, so I hope you enjoyed this video, and next week we're gonna look at a new kind of demonstration. Have a good one.